Hey, welcome back. In this video, we're going to talk about the technique of polynomial long division and some theorems associated with polynomial long division that will help us find the zeros for higher degree polynomials. First and foremost, we need to be able to perform long division of polynomials, which I have here. And what we're going to use generally is the same longhand technique we have for long division with regular numbers, and I'll give you an example there in 1 second. So we're going to set this up with the divisor of x plus 3 on the outside, and we're dividing into this cubic polynomial, 4x cubed minus 9x squared minus 58x plus 15. And the general cell is we're going to use, again, the same technique we use for long division with numbers. And so let's just do a quick example over here to set us straight. Let's say we want to take 315 and divide that by 5. In order to perform this, again, we put the divisor of 5 here on the outside. We're dividing into 315. I'll go through this pretty quickly, but just to illuminate the same moves that we're going to do over here with polynomials. 5 doesn't go into 3, 5 goes into 36 times. So I've decided how many times this 5 goes into here. 6 times 5 is 30. What I'm going to do is now calculate the remainder of that step right there. I'm going to subtract 30 from that result, and that gives me a 1. Bring down the 5, and now I just repeat that same process. The question is how many times does 5 go into 15? That answer is 3 times. 3 times 5 is 15. This works out really well, because it's working out perfectly in this division, giving me a remainder of 0. This 0 is really important. This means that 5 divides 315 evenly, but we'll come back and talk more about this of what do we do if we have a non-zero remainder. Also, as we know, there's an important link between division and multiplication. What we just calculated was that 315 divided by 5 equals 63. But equivalent and often more useful is the fact that we know then that 315 equals 63 times 5. So then we're going to divide these polynomials in the exact same manner. It's going to feel a bit different because we have these multiple terms and we have polynomials instead of just some real numbers like we do over there. But the general plan of attack is this, asking how many times does this go into these first terms? The beauty of this process is you only have to chase the lead terms. So in this first question right here, I'm asking how many times does x, the lead term of the divisor, go into 4x cubed? Often, once you get used to this process, what you want to write here is what gets multiplied by this, or how many times it goes into this will be automatic. In this case, for instance, right here, I know that what I'm looking for is 4x squared, because 4x squared times x does equal 4x cubed. But let's just say that wasn't obvious to you, you didn't see it right away. One thing that you can always do when asking that question is just take these and divide them from each other. So if I'm looking what times x equals 4x cubed, we'll simply take 4x cubed and divide it by x. And in this case, that result would be 4x squared, meaning 4x squared times x equals 4x cubed. But again, after doing this a bunch, you probably won't have to do a ton of those. But if you're ever confused or have a question, you can always do a quick division of the two lead terms. All right, so there's that first process. We've decided what we're multiplying by. Again, how many times does this term go into this term? Now what we're going to do is to multiply the 4x squared by this divisor x plus 3. Importantly here, since there are two terms, I'm using distribution, multiplying each of those terms. 4x squared times x is 4x cubed. That's what we're looking for. 4x squared times positive 3 is plus 12x squared. Now becomes the important trick right here, and it's why I used pink to denote this subtraction over there. We don't have to deal with distribution of a negative or anything like that with real numbers. But importantly here, what I want to do now is subtract this whole resulting polynomial here by this one above here. And so I'm subtracting that which means I need to subtract each term. In other words, distribute this negative to both of those. In this case, I have 4x cubed minus 4x cubed. Well, those cancels. That's exactly what I'm looking for. That's the reason I chose that 4x squared. Now I have negative 9x squared minus 12x squared. Or in other words, negative 9x squared and a negative 12x squared results in a negative 21x squared. The next step then is to bring down my next term. So I have negative 58x. And I repeat that exactly the same process. The question I'm asking now is, how many times does x go into negative 21x squared? Again, I'm thinking what times the x results in exactly this right here. And that would be negative 21x. Negative 21x times x is negative 21x squared. Exactly what I'm looking for. Negative 21x times a positive 3 would be a negative 63x. And then I'm going to divide here just to see how much of a remainder I have from this step right here. Negative 21x squared plus 21x squared, those cancel as they should. And now I have negative 58x, but now plus 63x, again, because this negative is distributing to both of these terms. That's always really important. So in other words, this is a negative 58x plus a 63. These have a difference of 5. So this is 5x. And I bring down my last term here of 15. So we have the process down. We just have one last step. Again, the question is, what times x is 5x? This one's pretty straightforward. Plus 5, which gives me 5x. And then a plus 15. This will work out perfectly. Importantly, this last line, since this is my last term, is just like this. Feeling good because now when I subtract these, because I'm subtracting a polynomial from itself, I know this results in a 0. Since we have a remainder of 0, this divides nice and evenly. Then what we get then, that 4x cubed minus 9x squared minus 58x plus 15 divided by x plus 3 equals 4x squared minus 21x plus 5. And as said previously, while this statement is really important, actually the factored version of this is the most important for us moving forward. So since we know that this cubic divided x plus 3 ends up being this quadratic, well, we also know that means that this quadratic times x plus 3 equals this. Or in other words, we've just found, and again, this will be the power of these moves here moving forward, is that 4x cubed minus 9x squared minus 58x plus 15 equals 4x squared minus 21x plus 5 times 3, or x plus 3, excuse me. And therefore, why this is such a powerful and important technique is that we can take cubics or polynomials of degree even higher, 3, 4, and 5, if we, through long division and other properties, can identify a 0 or 2 or a factor, then what we can do is take our cubic in this case. We've lessened the degree of what we're trying to work with. In this case, we've pulled out this linear factor right here. We have this quadratic. Now, if we can simply factor this quadratic, we can completely factor this cubic. And at this point, you probably have had a lot of experience factoring quadratics, but just walking through this real fast, I'll just use the guess and check method here to factor these. So I'm looking for two numbers in this first term that multiply to be the 4x squared. And then I got this constant term of plus 5. So if I have a 4x here and an x here, those multiply to give me my 4x squared. For the 5, it would be a 1 and a 5. I'm going to put the 5 over here because the 4x times the 5 will give me a negative 20. That's going to get me really close to this negative 21. So I want a minus there, and then a minus 1, negative 1 and negative 5 equals 5. And we get minus 20 and a minus 21. So this is the factored form there. So thus, what we've done using long division is taking this cubic, we've factored out this x plus 3 using long division. Then we get the result of this x plus 3 times a quadratic. We factor the quadratic, and now we've completely factored this cubic. And importantly, for application down the road, we now know that this has the zeros of x equals, this gives 1/4, this gives a 5, and this factor is a -3. All right, in the second example, we're going to do exactly the same thing, and I'll go through this fairly quickly, but I want to emphasize what to do if we don't have a remainder of 0. So just to illuminate this real fast, let's take a division of, say, 41 divided by 3. Quickly going through this, 3 goes into 4 1 times, which gives me a 3. Subtract that to get 1, bring down the 1. 3 goes into 11 3 times, which gives me a 9, and now this doesn't end perfectly, I get a 2. There's importantly several different ways of writing the result here. So one way of writing this is by saying is that 41 divided by 3 equals 13 2/3. The way I generate the 2/3 here is I take my remainder and I divide it by my divisor. So then we found that 41 divided by 3 is 13 2/3. Importantly, we have this alternate way of writing this that we want to focus on. Actually, if we multiply both sides of the expression by 3, we can get this more expanded version, or written in multiplication instead of division. Before I do that, just to illuminate this, just to make sure that we know this notation, that when you write 13 2/3, what you actually mean is 13 plus 2/3. But if I now multiply both sides of this by 3, it results in this statement right here, is that 41 equals 13 times 3 plus 2. Again, there's a couple ways to think about this, but what I'm doing right here in my thinking from this statement, which comes clearly from the division, is I'm multiplying this 13 by 3 and the 2/3 by a 3, resulting in 13 times 3 plus 2. But another way of thinking about this is just like thinking and looking at what the work I did right here, is that 3 went into 41 13 times with 2 left over. So I still had 2 to add on. So this ends up being 39 plus the 2 will result in the 41. But importantly here, when I have this 13, we call this the quotient. This is the result of the division. The 3 played the role of the divisor, and the 2 is the remainder. All right, let's now do the fun of doing the polynomial long division, and my goal is to get both of these versions right here. This will be the most important moving forward. But to divide these, and we'll do this fairly quickly, since we talked about the mechanics of this already, I'm going to divide 5x squared minus 12x minus 8 by the x plus 3. X goes into 5x squared, 5x times, that gives me a 5x squared. Everything looks good. 5x times 3 is a plus 15x. Just making sure I'm highlighting here. Remember to subtract this and not screw it up. 5x squared minus 5x squared, those cancel as they should. Negative 12x minus 15, this gives me a negative 27x. Bring down the negative 8, and now we start the process over again. The question is what do I multiply by x to get negative 27x? That seems pretty straightforward. Minus 27 to give me negative 27x. Negative 27 times 3 here is negative 81. Then I'm subtracting these from each other to find out how much is left over. It's pretty obvious that I'm not going to get a 0 here. So negative 27x plus 27x, those cancel. Now I have a negative 8 and a positive 81. Those add together to be 73. So then, one way of writing what I've just discovered is that 5x squared minus 12x minus 8 divided by x plus 3 equals 5x minus 27. So this is that quotient I have right here. And then I can write the remainder as 73 divided by my divisor. So my remainder divided by my divisor. Importantly, with polynomials, I do need to make sure I separate these with an addition, make that explicit. And I could write that just like this. And then finally, to write this alternate version right here, that will be an important move for us. I can think of multiplying both sides and both terms of both sides of this equation by this x plus 3. And this gives us the statement that 5x squared minus 12x minus 8 equals 5x minus 27. Now times x plus 3 with the remainder of 73. So following the second example, we're going to introduce the division algorithm, which simply says the existence of a statement right here. And so what this statement is saying, d of x is this divisor function right here, is that if we have a function, a divisor, and if that degree is less than this is really important, so that statement is made right here. The degree of the divisor is less than the degree of the function you're dividing here. So if this is of less degree than this, then we know there exists a quotient function and a remainder function to complete this statement right here. So generally written, so we know then that this quotient and remainder exists such that the function equals this quotient function, 5x minus 27 in this case, times this divisor function right here, d of x, so in our case that's x plus 3, plus the remainder. So for us, as we go through precalculus, the important thing about the division algorithm is just this statement right here, and to understand the relationship between the quotient, divisor, and the remainder. Though, at this point, we do have an important theorem that follows from this, and that's called the remainder theorem. Let me write it up here, and then I'll discuss with this example what exactly this is saying. So the remainder theorem states that if we have a polynomial function that has a degree of 1 or bigger, and then we have this number c, then we take our polynomial function and we divide that by this x minus c right here. So the factor is x minus whatever this c value is. Then the remainder of that operation is p of c right here, or what you'd get if you plugged that constant into the original function. So let's use this example we just did the division for to give some context to what the heck this is saying. So to apply the concept in this remainder theorem to what we have here, this p of x is this function we're dividing from, and so we're going to use this 5x squared minus 12x minus 8 right there. And we're going to divide by this x minus c. In this case, what we're going to do to use this example, we're going to let c equals negative 3. And we're going to use negative 3's because this is x minus negative 3. And we'll talk more about that in this future examples and future videos. So we have our setup with our polynomial of degree 1 or larger, and we have this c value right here. Now I'm going to borrow this statement right here. So we have the statement that 5x squared minus 12x minus 8 divided by, and now just to make it really clear, I'm going to rewrite x plus 3 as x minus negative 3. Again, because this is this divided by x minus c. We know that that was 5x minus 27, and then we had this remainder of 73, and we divide it by our divisor. The important statement is this right here. So what the remainder theorem is saying is that if we divided this polynomial by x minus this c value right here, then whatever that remainder is must be the value of plugging a negative 3 into this function right here. So we know that given this polynomial, if we plug in a negative 3, we're going to get out a 73. So don't get your mind too wound up on understanding this remainder theorem, though it is really important. It has consequences, especially to the factor theorem that we have coming up very soon. But I want to just describe what's going on here again and say why this is happening. So again, we have this polynomial function, 5x squared minus 12x minus 8. We know that that function can be rewritten in this kind of semi-factored form here, where we have this factored term, and then we have our remainder. If you think about this function right here in this form right here, and you think about plugging in the value of -3, because this -3 makes this factor right here 0, we're going to get 0 times who the heck cares what comes out of this, because I'm multiplying this result times 0. The result will be just this remainder right here. So importantly, this remainder theorem really follows directly from the division algorithm, meaning if you divide by something here, but you're thinking about a number that makes that divisor 0, this part will go to 0 and you'll just get out this number if you plug that x value into the original function. But importantly for us, this is going to have significant consequences and give us the factor theorem, which will be hugely important moving forward.